operations in it. So far, we talked about authentication. We saw how someone can gain access to a cluster. We saw different ways that someone, a human or a machine, can get access to the cluster. Once they gain access, what can they do? That's what authorization defines. First of all, why do you need authorization in your cluster? As an administrator of the cluster, we were able to perform all sorts of operations in it, such as viewing various objects like pods and nodes and deployments, creating or deleting objects, such as adding or deleting pods or even nodes in the cluster. As an admin, we are able to perform any operation. But soon, we will have others accessing the cluster as well, such as the other administrators, developers, testers, or other applications like monitoring applications or continuous delivery applications like Jenkins, etc. So we will be creating accounts for them to access the cluster by creating usernames and passwords or tokens or signed TLS certificates or service accounts as we saw in the previous lectures. But we don't want all of them to have the same level of access as us. For example, we don't want the developers to have access to modify our cluster configuration like adding or deleting nodes, or the storage or networking configurations. We can allow them to view but not modify, but they could have access to deploying applications. The same goes with service accounts. We only want to provide the external application the minimum level of access to perform its required operations. When we share our cluster between different organizations or teams by logically partitioning it using namespaces, we want to restrict access to the users to their namespaces alone. That is what authorization can help you within the cluster. There are different authorization mechanisms supported by Kubernetes, such as node authorization, attribute-based authorization, role-based authorization, and webhook. Let us go through these now. We know that the Kube API server is accessed by users like us for management purposes, as well as the kubelets on nodes within the cluster for management purposes within the cluster. The kubelet accesses the API server to read information about services, endpoints, nodes, and pods. The kubelet also reports to the Kube API server with information about the node, such as its status. These requests are handled by a special authorizer known as the node authorizer. In the earlier lectures, when we discussed about certificates, we discussed that the kubelets should be part of the system nodes group and have a name prefixed with system node. So any request coming from a user with the name system node and part of the system nodes group is authorized by the node authorizer and are granted these privileges. The privileges required for a kubelet. So that's access within the cluster. Let's talk about external access to the API. For instance, a user. Attribute-based authorization is where you associate a user or a group of users with a set of permissions. In this case, we say the dev user can view, create, and delete pods. You do this by creating a policy file with a set of policies defined in a JSON format this way. You pass this file into the API server. Similarly, we create a policy definition file for each user or group in this file. Now, every time you need to add or make a change in the security, you must edit this policy file manually and restart the Kube API server. As such, the attribute-based access control configurations are difficult to manage. We will look at role-based access controls next. Role-based access controls make these much easier. With role-based access controls, instead of directly associating a user or a group with a set of permissions, we define a role. In this case, for developers, we create a role with the set of permissions required for developers. Then we associate all the developers to that role. Similarly, create a role for security users with the right set of permissions required for them. Then associate the user to that role. Going forward, whenever a change needs to be made to the user's access, we simply modify the role and it reflects on all developers immediately. Role-based access controls provide a more standard approach to managing access within the Kubernetes cluster. We will look at role-based access controls in much more detail in the next lecture. For now, let's proceed with the other authorization mechanisms. Now, what if you want to outsource all the authorization mechanisms? Say you want to manage an authorization externally and not through the built-in mechanisms that we just discussed. For instance, Open Policy Agent is a third-party tool that helps with admission control and authorization. You can have Kubernetes make an API call to the Open Policy Agent with the information about the user and his access requirements, and have the Open Policy Agent decide if the user should be permitted or not. Based on that response, the user is granted access. Now, there are two more modes in addition to what we just saw: always allow and always deny. As the name states, always allow allows all requests without performing any authorization checks. Always deny denies all requests. So where do you configure these modes? Which of them are active by default? Can you have more than one at a time? How does authorization work if you do have multiple ones configured? The modes are set using the authorization mode option on the Kube API server. If you don't specify this option, it is set to always allow by default. You may provide a comma-separated list of multiple modes that you wish to use. In this case, I want to set it to Node, RBAC, and Webhook. When you have multiple modes configured, your request is authorized using each one in the order it is specified. For example, when a user sends a request, it's first handled by the node authorizer. The node authorizer handles only node requests, so it denies the request. Whenever a module denies a request, it is forwarded to the next one in the chain. The role-based access control module performs its checks and grants the user permission. Authorization is complete and user is given access to the requested object. So, every time a module denies a request, it goes to the next one in the chain, and as soon as a module approves the request, no more checks are done and the user is granted permission. Well, that's it for this lecture. In the upcoming lectures, we will discuss more about role-based access controls. In this lecture, we look at role-based access controls in much more detail. So how do we create a role? We do that by creating a role object. So we create a role definition file with the API version set to rbac.authorization.k8.io/v1 and kind set to role. We name the role developer as we are creating this role for developers. And then we specify rules. Each rule has three sections: API groups, resources, and verbs. The same things that we talked about in one of the previous lectures. For core group, you can leave the API groups section as blank. For any other group, you specify the group name. The resources that we want to give developers access to are pods. The actions that they can take are list, get, create, and delete. Similarly, to allow the developers to create config maps, we add another rule to create config map. You can add multiple rules for a single role like this. Create the role using the kubectl create role command. The next step is to link the user to that role. For this, we create another object called role binding. The role binding object links a user object to a role. We will name it dev user to developer binding. The kind is role binding. It has two sections. The subjects is where we specify the user details. The role ref section is where we provide the details of the role we created. Create the role binding using the kubectl create command. Also note that the roles and role bindings fall under the scope of namespaces. So here, the dev user gets access to pods and config maps within the default namespace. If you want to limit the dev user's access within a different namespace, then specify the namespace within the metadata of the definition file while creating them. To view the created roles, run the kubectl get roles command. To list role bindings, run the kubectl get role bindings command. To view more details about the role, run the kubectl describe role developer command. Here you see the details about the resources and permissions for each resource. Similarly, to view details about role bindings, run the kubectl describe role bindings command. Here you can see details about an existing role binding. What if you, being a user, would like to see if you have access to a particular resource in the cluster? You can use the kubectl auth cani command and check if you can, say, create deployments or say delete nodes. If you're an administrator, then you can even impersonate another user to check their permission. For instance, say you were tasked to create necessary set of permissions for a user to perform a set of operations, and you did that, but you would like to test if what you did is working. You don't have to authenticate as the user to test it. Instead, you can use the same command with the as user option like this. Since we did not grant the developer permissions to create deployments, it returns no. The dev user has access to creating pods though. You can also specify the namespace in the command like this. The dev user does not have permission to create a pod in the test namespace. Well, a quick note on resource names. We just saw how you can provide access to users for resources like pods within the namespace. You can go one level down and allow access to specific resources alone. For example, say you have 5 pods in namespace. You want to give access to a user to pods, but not all pods. You can restrict access to the blue and orange pod alone by adding a resource names field to the rule. Well, that's it for this lecture. Head over to the practice exercises section and practice working with role-based access controls. We discussed about roles and role bindings in the previous lecture. In this lecture, we will talk about cluster roles and cluster role bindings. When we talked about roles and role bindings, we said that roles and role bindings are namespaced, meaning they are created within namespaces. If you don't specify a namespace, they're created in the default namespace and control access within that namespace alone. In one of the previous lectures, we discussed about namespaces and how it helps in grouping or isolating resources like pods, deployments, and services. But what about other resources like nodes? Can you group or isolate nodes within a namespace? Like, can you say node 01 is part of the dev namespace? No. Those are cluster-wide or cluster-scoped resources. They cannot be associated to any particular namespace. So the resources are categorized as either namespaced or cluster-scoped. Now, we have seen a lot of namespaced resources throughout this course, like pods and replica sets and jobs, deployments, services, secrets. And in the last lecture, we saw 2 new roles and role bindings. These resources are created in the namespace you specify when you create them. If you don't specify a namespace, they are created in the default namespace. To view them or delete them or update them, you always specify the right namespace. The cluster scoped resources are those where you don't specify a namespace when you create them, like nodes, persistent volumes, the cluster roles and cross-cluster role bindings that we're going to look at in this lecture. Certificate signing requests we saw earlier, and namespace objects themselves are, of course, not namespaced. Note that this is not a comprehensive list of resources. To see a full list of namespaced and non-namespaced resources, run the kubectl API resources command with the namespaced option set. In the previous lecture, we saw how to authorize a user to namespace resources. We use roles and role bindings for that. But how do we authorize users to cluster-wide resources like nodes or persistent volumes? That is where you use cluster roles and cluster role bindings. Cluster roles are just like roles, except they are for cluster-scoped resources. For example, A cluster admin role can be created to provide a cluster administrator permissions to view, create, or delete nodes in a cluster. Similarly, a storage administrator role can be created to authorize a storage admin to create persistent volumes and claims. Create a cluster role definition file with the kind cluster role and specify the rules as we did before. In this case, the resources are nodes, then create the cluster role. The next step is to link the user to that cluster role. For this, we create another object called cluster role binding. The role binding object links the user to the role. We will name it cluster admin role binding. The kind is cluster role binding. Under subjects, we specify the user details, cluster admin user in this case. The role ref section is where we provide the details of the cluster role we created. Create the role binding using the kubectl create command. One thing to note before I let you go. We said that cluster roles and bindings are used for cluster scope resources, but that is not a hard rule. You can create a cluster role for namespace resources as well. When you do that, the user will have access to these resources across all namespaces. Earlier, when we created a role to authorize a user to access pods, the user had access to the pods in a particular namespace alone. With cluster roles, when you authorize a user to access the pods, the user gets access to all pods across the cluster. Kubernetes creates a number of cluster roles by default when the cluster is first set up. We will explore those in the practice tests that are coming up. Good luck. Hello and welcome to this lecture. In this lecture, we will talk about service accounts in Kubernetes. The concept of service accounts is linked to other security-related concepts in Kubernetes, such as authentication, authorization, role-based access controls, etc. However, as part of the Kubernetes for the Application Developers exam curriculum, you only need to know how to work with service accounts. We have detailed sections covering the other concepts in security in the Kubernetes Administrators course. So there are two types of accounts in Kubernetes, a user account and a service account. As you might already know, the user account is used by humans and service accounts are used by machines. A user account could be for an administrator accessing the cluster to perform administrative tasks, or a developer accessing the cluster to deploy applications, etc. A service account could be an account used by an application to interact with the Kubernetes cluster. For example, a monitoring application like Prometheus uses a service account to poll the Kubernetes API for performance metrics. An automated build tool like Jenkins uses service accounts to deploy applications on the Kubernetes cluster. Let's take an example. I've built a simple Kubernetes dashboard application named My Kubernetes Dashboard. It's a simple application built in Python, and all that it does when deployed is retrieve the list of pods on a Kubernetes cluster by sending a request to the Kubernetes API and display it on a web page. In order for my application to query the Kubernetes API, it has to be authenticated. For that, we use a service account. To create a service account, run the command kubectl create service account followed by the account name, which is dashboard-sa in this case. To view the service accounts, run the kubectl get service account command. This will list all the service accounts. When the service account is created, it also creates a token automatically. The service account token is what must be used by the external application while authenticating to the Kubernetes API. The token, however, is stored as a secret object. In this case, it's named dashboard-sa-token-kbpdm. So when a service account is created, it first creates the service account object and then generates a token for the service account. It then creates a secret object and stores that token inside the secret object. The secret object is then linked to the service account. To view the token, view the secret object by running the command kubectl describe secret. This token can then be used as an authentication bearer token while making a REST call to the Kubernetes API. For example, in this simple example using curl, you could provide the bearer token as an authorization header while making a REST call to the Kubernetes API. In case of my custom dashboard application, copy and paste the token into the tokens field to authenticate the dashboard application. So that's how you create a new service account and use it. You can create a service account, assign the right permissions using role-based access control mechanisms, which is out of scope for this course, and export your service account tokens and use it to configure your third-party application to authenticate to the Kubernetes API. But what if your third-party application is hosted on the Kubernetes cluster itself? For example, we can have our custom Kubernetes dashboard application or the Prometheus application deployed on the Kubernetes cluster itself. In that case, this whole process of exporting the service account token and configuring the third-party application to use it can be made simple by automatically mounting the service token secret as a volume inside the pod hosting the third-party application. That way, the token to access the Kubernetes API is already placed inside the pod and can be easily read by the application. You don't have to provide it manually. If you go back and look at the list of service accounts, you will see that there is a default service account that exists already. For every namespace in Kubernetes, a service account named default is automatically created. Each namespace has its own default service account. Whenever a pod is created, the default service account and its token are automatically mounted to that pod as a volume mount. For example, we have a simple pod definition file that creates a pod using my custom Kubernetes dashboard image. We haven't specified any secrets or volume mounts in the definition file. However, when the pod is created, if you look at the details of the pod by running the kubectl describe pod command, you see that a volume is automatically created from the secret named default token, which is in fact the secret containing the token for this default service account. The secret token is mounted at location var run secrets kubernetes.io service account inside the pod. So from inside the pod, if you run the ls command to list the contents of the directory, you will see the secret mounted as 3 separate files. The one with the actual token is the file named token. If you view contents of that file, you will see the token to be used for accessing the Kubernetes API. Now remember that the default service account is very much restricted. It only has permission to run basic Kubernetes API queries. If you'd like to use a different service account, such as the one we just created, modify the pod definition file to include a service account field and specify the name of the new service account. Remember, you cannot edit the service account of an existing pod. You must delete and recreate the pod. However, in case of a deployment, you will be able to edit the service account, as any changes to the pod definition file will automatically trigger a new rollout for the deployment. So the deployment will take care of deleting and recreating new pods with the right service account. When you look at the pod details now, you see that the new service account is being used. So remember, Kubernetes automatically mounts the default service account if you haven't explicitly specified any. You may choose not to mount a service account automatically by setting the Auto Mount Service Account Token field to false in the pod specs section. Let's now discuss some of the changes that were made in releases version 1.22 and 1.24 of Kubernetes that changed the way service accounts, secrets, and tokens worked. Now, as we discussed in the previous video, every namespace has a default service account, and that service account has a secret object with a token associated with it. When a pod is created, it automatically associates the service account to the pod and mounts the token to a well-known location within the pod. In this case, it's under a var run secrets kubernetes.io/service account. This makes the token accessible to a process that's running within the pod, and that enables that process to query the Kubernetes API. Now, if you list the contents of the directory inside the pod, you will see the secret mounted as 3 separate files. The one with the actual token is the file named token. So if you list the contents of that file, you'll see the token to be used for accessing the Kubernetes API. So all of that remains same. This is exactly what we discussed in the previous video. Now, let's take that token that we just saw, and if you decode this token using this command, or you could just copy and paste this token in the JWT website at jwt.io, you'll see that it has no expiry date defined in the payload section here on the right. So this is a token that does not have an expiry date set. So this excerpt from the Kubernetes enhancement proposal for creating bound service account tokens describes this form of JWT to be having some security and scalability related issues. So the current implementation of JWT is not bound to any audience and is not time bound, as we just saw. There was no expiry date for the token. So the JWT is valid as long as the service account exists. Moreover, each JWT requires a separate secret object per service account, which results in scalability issues. And as such, in version 1.22, the token request API was introduced as part of the Kubernetes enhancement proposal 1205 that aimed to introduce a mechanism for provisioning Kubernetes service account tokens that are more secure and scalable via an API. So tokens generated by the token request API are audience bound, they're time bound, and object bound, and hence are more secure. Now, since version 1.22, when a new pod is created, it no longer relies on the service account secret token that we just saw. Instead, a token with a defined lifetime is generated through the token request API by the service account admission controller when the pod is created, and this token is then mounted as a projected volume into the pod. So in the past, if you look at this space here, you'd see as the secret that's part of the service account mount as a secret object, but now as you can see, it's a projected volume that actually communicates with the token controller API, token request API, and it gets a token for the pod. Now, with version 1.24, another enhancement was made as part of the Kubernetes enhancement proposal 2799, which dealt with the reduction of secret-based service account tokens. So in the past, when a service account was created, it automatically created a secret with a token that has no expiry and is not bound to any audience. This was then automatically mounted as a volume to any pod that uses that service account, and that's what we just saw. But in version 1.22, that was changed. The automatic mounting of the secret object to the pod was changed, and instead it then moved to the token request API. So with version 1.24, a change was made where when you create a service account, it no longer automatically creates a secret or a token access secret. So you must run the command kubectl create token followed by the name of the service account to generate a token for that service account if you needed one. And it will then print that token on screen. Now, if you copy that token and then if you try to decode this token, this time you'll see that it has an expiry date defined. And if you haven't specified any time limit, then it's usually 1 hour from the time that you ran the command. You can also pass in additional options to the command to increase the expiry of the token. So now post version 1.24, if you would still like to create secrets the old way with non-expiring token, then you could still do that by creating a secret object with the type set to kubernetes.io/service-account-token and the name of the service account specified within annotations in the metadata section like this. So this is how the secret object will be associated with that particular service account. So when you do this, just make sure that you have the service account created first and then create a secret object. Otherwise, the secret object will not be created. So this will create a non-expiring token in a secret object and associate it with that service account. Now, you have to be sure if you really want to do that, because as per the Kubernetes documentation pages on service account token secrets, it says you should only create service account token secrets if you can't use the token request API to obtain a token. So that's either the kubectl create token command we just talked about, or it talks to the token request API to generate that token, or it's the automated token creation that happens on pods when they are created post version 1.22. And also, you should only create service account token request if the security exposure of persisting a non-expiring token credential is acceptable to you. Now, the token request API is recommended instead of using the service account token secret objects, as they are more secure and have a bounded lifetime, unlike the service account token request. In this lecture, we will talk about securing images. We will start with the basics of image names and then work our way towards secure image repositories and how to configure your pods to use images from secure repositories. We deployed a number of different kinds of pods hosting different kinds of applications throughout this course, like web apps and databases and Redis, cache, etc. Let's start with a simple pod definition file, for instance. Here we have used the nginx image to deploy an nginx container. Let's take a closer look at this image name. The name is nginx. But what is this image and where is this image pulled from? This name follows Docker's image naming convention. Nginx here is the image or the repository name. When you say nginx, it's actually library/nginx. The first part stands for the user or the account name. So if you don't provide a user or account name, it assumes it to be library. Library is the name of the default account where Docker's official images are stored. These images promote best practices and are maintained by a dedicated team who are responsible for reviewing and publishing these official images. Now, if you were to create your own account and create your own repositories or images under it, then you would use a similar pattern. So instead of library, it would be your name or your company's name. Now, where are these images stored and pulled from? Since we have not specified the location where these images are to be pulled from, it is assumed to be Docker's default registry, Docker Hub, the DNS name for which is docker.io. The registry is where all the images are stored. Whenever you create a new image or update an image, you push it to the registry, and every time anyone deploys this application, it is pulled from the registry. There are many other popular registries as well. Google's registry is at gcr.io, where a lot of Kubernetes related images are stored, like the ones used for performing end-to-end tests on the cluster. These are all publicly accessible images that anyone can download and access. When you have applications built in-house that shouldn't be made available to the public, hosting an internal private registry may be a good solution. Many cloud service providers such as AWS, Azure, or GCP provide a private registry by default. On any of these solutions, be it on Docker Hub or Google's registry or your internal private registry, you may choose to make a repository private so that it can be accessed using a set of credentials. From Docker's perspective, to run a container using a private image, you first log in to your private registry using the docker login command. Input your credentials. Once successful, run the application using the image from the private registry. Going back to our pod definition file, to use an image from our private registry, we replace the image name with the full path to the one in the private registry. But how do we implement the authentication, the login part? How does Kubernetes get the credentials to access the private registry? Within Kubernetes, we know that the images are pulled and run by the Docker runtime on the worker nodes. How do you pass the credentials to the Docker runtimes on the worker nodes? For that, we first create a secret object with the credentials in it. The secret is of type Docker registry, and we name it regcred. Docker registry is a built-in secret type that was built for storing Docker credentials. We then specify the registry server name, the username to access the registry, the password, and the email address of the user. We then specify the secret inside our pod definition file under the image pull secret section. When the pod is created, Kubernetes, or the kubelets on the worker node, uses the credentials from the secret to pull images. Well, that's it for this lecture. Head over to the practice exercises section and practice working with secure images. Hello and welcome to this lecture. In this lecture, we will talk about security contexts in Kubernetes. But before we get into that, it is important to have some knowledge about security in Docker. If you are familiar with security in Docker, feel free to skip this lecture and head over to the next. In this lecture, we will look at the various concepts related to security in Docker. Let us start with a host with Docker installed on it. This host has a set of its own processes running, such as a number of operating system processes, the Docker daemon itself, the SSH server, etc. We will now run an Ubuntu Docker container that runs a process that sleeps for an hour. We have learned that unlike virtual machines, containers are not completely isolated from their host. Containers and the host share the same kernel. Containers are isolated using namespaces in Linux. The host has a namespace and the containers have their own namespace. All the processes run by the containers are in fact run on the host itself, but in their own namespace. As far as the Docker container is concerned, it is in its own namespace and it can see its own processes only. It cannot see anything outside of it or in any other namespace. So when you list the processes from within the Docker container, you see the sleep process with a process ID of 1. For the Docker host, all processes of its own as well as those in the child namespaces are visible as just another process in the system. So when you list the processes on the host, you see a list of processes including the sleep command but with a different process ID. This is because the processes can have different process IDs in different namespaces, and that's how Docker isolates containers within a system. So that's process isolation. Let us now look at users in context of security. The Docker host has a set of users, a root user as well as a number of non-root users. By default, Docker runs processes within containers as the root user. This can be seen in the output of the commands we ran earlier. Both within the container and outside the container on the host, the process is run as the root user. Now, if you do not want the process within the container to run as the root user, you may set the user using the user option within the Docker run command and specify the new user ID. You will see that the process now runs with the new user ID. Another way to enforce user security is to have this defined in the Docker image itself at the time of creation. For example, we will use the default Ubuntu image and set the user ID to 1000 using the user instruction. Then build the custom image. We can now run this image without specifying the user ID, and the process will be run with the user ID 1000. Let us take a step back. What happens when you run containers as the root user? Is the root user within the container the same as the root user on the host? Can the process inside the container do anything that the root user can do on the system? If so, isn't that dangerous? Well, Docker implements a set of security features that limits the abilities of the root user within the container. So the root user within the container isn't really like the root user on the host. Docker uses Linux capabilities to implement this. As we all know, the root user is the most powerful user on a system. The root user can literally do anything, and so does a process run by the root user. It has unrestricted access to the system, from modifying files and permissions on files, access control, creating or killing processes, setting group ID or user ID, performing network-related operations such as binding to network ports, broadcasting on a network, controlling network ports, system-related operations like rebooting the host, manipulating system clock, and many more. All of these are the different capabilities on a Linux system, and you can see a full list at this location. You can now control and limit what capabilities are made available to a user. By default, Docker runs a container with a limited set of capabilities, and so the processes running within the container do not have the privileges to, say, reboot the host or perform operations that can disrupt the host or other containers running on the same host. If you wish to override this behavior and provide additional privileges than what is available, use the cap add option in the docker run command. Similarly, you can drop privileges as well using the cap drop option. Or in case you wish to run the container with all privileges enabled, use the privileged flag. Well, that's it on Docker security for now. I will see you in the next lecture. Hello and welcome to this lecture on security context in Kubernetes. My name is Mumshad Manambeth. As we saw in the previous lecture, when you run a Docker container, you have the option to define a set of security standards, such as the ID of the user used to run the container, the Linux capabilities that can be added or removed from the container, etc. These can be configured in Kubernetes as well. As you know already, in Kubernetes, containers are encapsulated in pods. You may choose to configure the security settings at a container level or at a pod level. If you configure it at a pod level, the settings will carry over to all the containers within the pod. If you configure it at both the pod and the container, the settings on the container will override the settings on the pod. Let us start with a pod definition file. This pod runs an Ubuntu image with the sleep command. To configure security context on the container, add a field called security context under the specs section of the pod. Use the run as user option to set the user ID for the pod. To set the same configuration on the container level, move the whole section under the container specification like this. To add capabilities, use the capabilities option and specify a list of capabilities to add to the pod. Well, that's all on security context in Kubernetes. Head over to the coding exercises section and practice viewing, configuring, and troubleshooting issues related to security contexts in Kubernetes. That's it for now, and I will see you in the next lecture. Hello, and welcome to this lecture on network policies. So let us first get our networking and security basics right. And I'm sorry if this is too basic, but I just wanted to spend a minute on this to make sure we're all on the same page before we begin. We will start with a simple example of a traffic flowing through a web, app, and database server. So you have a web server serving front-end to users, an app server serving back-end APIs, and a database server. The user sends in a request to the web server at port 80, The web server then sends a request to the API server at port 5000 in the backend. The API server then fetches data from the database server at port 3306 and then sends the data back to the user. A very simple setup. So there are two types of traffic here, ingress and egress. For example, for a web server, the incoming traffic from the users is an ingress traffic, and the outgoing request to the app server is egress traffic, and that is denoted by the straight arrow. When you define ingress and egress, remember you're only looking at the direction in which the traffic originated. The response back to the user, denoted by the dotted lines, do not really matter. Similarly, in case of the backend API server, it receives ingress traffic from the web server on port 5000 and has egress traffic to port 3306 to the database server. And from the database server's perspective, it receives ingress traffic on port 3306 from the API server. If we were to list the rules required to get this working, we would have an ingress rule that is required to accept HTTP traffic on port 80 on the web server, an egress rule to allow traffic from the web server to port 5000 on the API server, an ingress rule to accept traffic on port 5000 on the API server, and an egress rule to allow traffic to port 3306 on the database server. And finally, an ingress rule on the database server to accept traffic on port 3306. So that's the basic of traffic flow and rules. Let us now look at network security in Kubernetes. So we have a cluster with a set of nodes hosting a set of pods and services. Each node has an IP address, and so does each pod, as well as service. One of the prerequisites for networking in Kubernetes is whatever solution you implement, the pods should be able to communicate with each other without having to configure any additional settings like routes. For example, in this network solution, all pods are on a virtual private network that spans across the nodes in the Kubernetes cluster, and they can all by default reach each other using the IPs or pod names or services configured for that purpose. Kubernetes is configured by default with an all-allow rule that allows traffic from any pod to any other pod or services within the cluster. Let us now bring back our earlier discussion and see how it fits into Kubernetes. For each component in the application, we deploy a pod, one for the front-end web server, for the API server, and one for the database. We create services to enable communication between the pods as well as to the end user. Based on what we discussed in the previous slide, by default, all the three pods can communicate with each other within the Kubernetes cluster. What if we do not want the front-end web server to be able to communicate with the database server directly? Say, for example, your security teams and audits require you to prevent that from happening. That is where you would implement a network policy to allow traffic to the DB server only from the API server. A network policy is another object in the Kubernetes namespace, just like pods, replica sets, or services. You link a network policy to one or more pods. You can define rules within the network policy. In this case, I would say only allow ingress traffic from the API pod on port 3306. Once this policy is created, it blocks all other traffic to the pod and only allows traffic that matches the specified rule. Again, this is only applicable to the pod on which the network policy is applied. So how do you apply or link a network policy to a pod? We use the same technique that was used before to link replica sets or services to pods, labels and selectors. We label the pod and use the same labels on the port selector field in the network policy. And then we build our rule. Under policy types, specify whether the rule is to allow ingress or egress traffic or both. In our case, we only want to allow ingress traffic to the DB pod, so we add ingress. Next, we specify the ingress rule that allows traffic from the API pod, and you specify the API pod, again using labels and selectors, and finally the port to allow traffic on, which is 3306. Let us put all that together. We start with a blank object definition file, and as usual we have API version, kind, metadata, and spec. The API version is networking.k8s.io/v1. The kind is network policy. We will name the policy db-policy, and then under the spec section, we will first move the pod selector to apply this policy to the DB pod. Then we will move the rule we created in the previous slide under it. And that's it. We have our first network policy ready.
Now, note that ingress or egress isolation only comes into effect if you have ingress or egress in the policy types. In this example, there's only ingress in the policy type, which means only ingress traffic is isolated and all egress traffic is unaffected, meaning the pod is able to make any egress calls and they're not blocked. So for an egress or ingress isolation to take place, note that you have to add them under the policy types as seen here. Otherwise, there is no isolation.
Run the kubectl create command to create the policy. Remember that network policies are enforced by the network solution implemented on Kubernetes cluster, and not all network solutions support network policies. A few of them that are supported are kuberouter, Calico, Romana, and WeaveNet. If you used Flannel as the networking solution, it does not support network policies as of this recording. Always refer to the network solutions documentation to see support for network policies. Also remember, even in a cluster configured with a solution that does not support network policies, you can still create the policies, but they will just not be enforced. You will not get an error message saying the network solution does not support network policies. Well, that's it for this lecture. Walk through the documentation and head over to the coding challenges to practice network policies. This lecture, we will take a look at network policies in more detail. So here we have the same web API and database pods that we discussed about in the previous lecture. So first, let's be very clear with our requirements. Our goal is to protect the database pod so that it does not allow access from any other pod except the API pod and only on port 3306. So let's assume that we are not concerned about the web pod or the API pod. For those pods, we are okay for all traffic to go in and out from anywhere. However, we want to protect the database pod and only allow traffic from the API pod. So let's get the other things out of our way so we can focus exactly on the required tasks. So we don't need to worry about the web pod or its port, as we don't want to allow any traffic from any other sources other than the API pod. So let's get rid of that. We can also forget about the port on the API pod to which the web server connects, as we don't care about that either. As we discussed, by default, Kubernetes allows all traffic from all pods to all destinations. So as the first step, we want to block out everything going in and out of the database pod. So we create a network policy. We will call it DB policy. And the first step is to associate this network policy with the pod that we want to protect. And we do that using labels and selectors. So we do that by adding a pod selector field with the match labels option and by specifying the label on the DB pod, which happens to be set to role DB. And that associates the network policy with the database pod and blocks out all traffic. However, we need the API pod to be able to query the database on port 3306. So that's what we are going to configure next. First, we need to figure out what type of policies should be defined on this network policy object to meet our requirements. So there are two types of policies that we discussed in the previous lecture. We have ingress and egress. So do we need ingress or egress here, or both? So you always look at this from the DB pod's perspective. From the DB pod's perspective, we want to allow incoming traffic from the API pod. So that is incoming, so that is ingress. The API pod makes database queries and the database pods returns the results. So what about the results? Do you need a separate rule for the results to go back to the API pod? No, because once you allow incoming traffic, the response or reply to that traffic is allowed back automatically. We don't need a separate rule for that. So in this case, all we need is an ingress rule to allow traffic from the API pod to the database pod. And that would allow the API pod to connect to the database and run queries and also retrieve the result of the queries. So when deciding on what type of rule is to be created, you only need to be concerned about the direction in which the request originates, which is denoted by the straight line here. And you don't need to worry about the response, which is denoted by the dotted line. However, this rule does not mean that the database pod will be able to connect to the API pod or make calls to the API. Say, for example, the database pod tries to make an API call to the API pod, then that would not be allowed because that is now an egress traffic originating from the database pod and would require a specific egress rule to be defined. So I hope you get the difference between the two and are clear about ingress and egress rules. I just wanted to make sure that you're clear on what type of policy is to be selected for the requirement that you have in hand. So a single network policy can have an ingress type of rule, an egress type of rule, or both in cases where a pod wants to allow incoming connections as well as wants to make external calls. So for now, our use case only requires ingress policy types. Now that we have decided on the type of policy, the next step is to define the specifics of that policy. If it's ingress, we create a section called ingress within which we can specify multiple rules. Each rule has a from and ports fields. The from field defines the source of traffic that is allowed to pass through to the database pod. And here we would use a pod selector and provide the labels of the API pod like this. The ports field defines what port on the database pod is the traffic allowed to go to. In this case, it's 3306 with the TCP protocol. And that's it. This would create a policy that would block all traffic to the DB pod except for traffic from the API pod. Now, what if there are multiple API pods in the cluster with the same labels but in different namespaces? So say here we have different namespaces for dev, test, and prod environments, and we have the API pod with the same labels in each of these environments. The current policy would allow any pod in any namespace with matching labels to reach the database pod. We only want to allow the API pod in the prod namespace to reach the database pod. So how do we do that? For this, we add a new selector called as the namespace selector property along with the pod selector property. Under this, we use match labels again to provide a label set on the namespace. And you must remember that you must have this label set on the namespace first for this to work. So that's what the namespace selector does. It helps in defining from what namespace traffic is allowed to reach the database pod. Now, what if you only have the namespace selector and not the pod selector like this? In this case, all pods within the specified namespace will be allowed to reach the database pod, such as the web pod that we had earlier. But pods from outside this namespace won't be allowed to go through. Let's look at another use case. Say we have a backup server somewhere outside of the Kubernetes cluster, and we want to allow this server to connect to the database pod. Now, since this backup server is not deployed in our Kubernetes cluster, the pod selector and namespace selector fields that we use to define traffic from won't work because it's not a pod in the cluster. However, we know the IP address of the backup server, and that happens to be 192.168.5.10. We could configure a network policy to allow traffic originating from certain IP addresses. For this, we add a new type of from definition known as the IP block definition. IP block allows you to specify a range of IP addresses from which you could allow traffic to hit the database pod. So those are three supported selectors under the from section and ingress. And these are also applicable to the to section in egress. And we'll see that in a few minutes. We have pod selector to select pods by labels. We have namespace selector to select namespaces by labels. And we have the IP block selector to select IP address ranges. These can be passed in separately as individual rules or together as part of a single rule. In this example, under the from section, we have two elements. So these are two rules. The first rule has the pod selector and the namespace selector together, and the second rule has the IP block selector. So this works like an OR operation. Traffic from sources meeting either of these criteria are allowed to pass through. However, within the first rule, we have two selectors part of it. That would mean traffic from sources must meet both of these criteria to pass through. So they have to be originating from pods with matching labels of API pod, and those pods must be in the prod namespace. So it works like an AND operation. Now, what if we were to separate them by adding a dash before the namespace selector like this? Now, they are two separate rules. So this would mean that traffic matching the first rule is allowed, that is, from any pod matching the label API pod in the same namespace, and traffic matching the second rule is allowed, which is from any pod within the prod namespace, that is either from the pod web. And of course, along with the backup server, as we have the IP block specification as well. So now we have three separate rules, and almost traffic from anywhere is allowed to the DB pod. So a small change like that can have a big impact. So it's important to understand how you could put together these rules based on your requirements. So now let's get rid of all of that and go back to a basic set of rules, and we'll now look at egress. So say, for example, instead of the backup server initiating a backup, say we have an agent on the DB pod that pushes backup to the backup server. In that case, the traffic is originating from the database pod to an external backup server. For this, we need to have egress rule defined. So we first add egress to the policy types, and then we add a new egress section to define the specifics of the policy. So instead of from, we now have to under egress. So that's the only difference. Under to, we could use any of the selectors such as a pod, a namespace, or an IP block selector. And in this case, since the database server is external, we use IP block selector and provide the CIDR block for the server. The port to which the requests are to be sent to is 80, so we specify 80 as the port. So this rule allows traffic originating from the database pod to an external backup server at the specified address. Well, that's it for now about network policies and rules. Head over to the lab and practice working with network policies yourself. I will see you in the next one.